are solving the first LeetCode task. To sum, we are given an integer array nums and one number target, and we need to check if in the given array nums there are two elements that add up to the target. So for example, if we have array 2, 7, 11 and 15 and target is number 9, we need to check if there are two elements that add up to 9. So in this case, these elements are 2 and 7, and we need to return their indexes as a result. So 0 and 1 in this case. Let's see the possible approaches here. So if you have, for example, array like this one, we start from the beginning, from element 2. And in the rest of array, we want to check if there is an element, another one, that 2 plus that element is equal to target 9. So we are searching for number 7. There is no number 7 in this array, so we are moving forward. We are moving our iterator from 2 to 6, from 0 position to the first one. And since we are dealing with number 6 now, we want to check if there is number 3 in the rest of array, because 6 plus 3 is 9, which is the target. And there is the 3 in this case. So we need to return their indexes. Let's see how the pseudocode for such solution will look like. So the first element, current one, is nums of I, and we are searching for element 2. So element 1 plus element 2 equals target. So we want to check if element 2, which is target, minus first element, if such element exists in the array. And if exists, we need to return indexes of element 1 and element 2. So how we can search for the second element in the array? We can iterate through the rest of array, so starting from I plus 1. For example, if we are here with index I, we want to iterate through the rest, so starting from I plus 1 to the end of array as well. And if nums of j is equal to element 2, we found it, and we need to return indexes I and j. Notice that this part is some kind of linear search. So we are dealing with element 6, and in this part of array, we are searching for number 3. That is our task. So this part is some kind of linear search, but not applied to whole array, but for just one part. But the complexity is same, big O of n. But let's see how we can do it faster. Binary search would have the complexity logarithm n, not n, which is better. So we could apply binary search, but only if we are dealing with a sorted array. Here we can have, for example, 3, 2, 4, and our array is not sorted initially. So we would need to sort our array first and then apply binary search. The problem with just sorting the array is that we can mix original indexes, but we need to return original indexes of our elements as a result. So we can sort the array, but make sure that save somehow information about original indexes. And you can, if you want to practice, you can implement the solution with binary search with first sort the array and save information about original indexes by some mapping. And this part would be logarithm complexity. But we can do it even better with constant time complexity. because if we use the first for loop to save elements of our original array in dictionary and also information about their indexes, here, instead of both binary and linear search, we can just check if our needed element exists in dictionary. And that operation is constant. So let's write pseudocode in detail for this solution. We can first initialize our dictionary with all elements and then iterate through elements and check if in dictionary we have already needed element. But here we can just use the same loop and the first element. And here, instead of this for loop and binary search, we can just check if dictionary contains element 2. And if yes, return indexes I and j. Here, it's important to take care that I and j should be different. So we want to return I and j only if I is different than j. And since our dictionary is a list of key value pairs, element, and their indexes, we are getting the index of our element as dictionary of L2. And we can apply this access because we are sure that our dictionary contains the key element 2. So let us discuss how we will implement this pseudocode, how we'll transform it to the C#. Here, it's clear that we are dealing with dictionary. We are creating a dictionary. So it is totally fine to use var instead the explicit type. We can add a new element in dictionary only if dictionary doesn't already contain that key. So we want to add a key value pair. And we want to check if element 2 exists in dictionary. So if dictionary contains key element 2, we are said that we will have exactly one solution for sure. So in some of iterations, we will come to this line and return the result. But we need to complete our function to design to cover all paths. So here we need to add the return statement, even though this part will be unreachable. Let's try to run and submit our code. We missed to add the semicolon at the end of the statement. Okay, good. Let us see the time and space complexity of this solution. So these expressions are constant in terms of time complexity. Here we have the for loop of n iterations, which is big O of n for now. But let us see what is happening inside the for loop. This is constant. This operation contains key is constant as well. Method contains key is constant because we have element 1. And dictionary works so that element is being transformed with some hash function to just one value. We have element 1, for example, 6, and we are transforming it by using some function. And we get some, let's say, index in memory. And by using that point in memory, we know exactly about the place in memory where we want to search for our element. This one is constant as well, and everything inside the for loop with this solution, with dictionary, is constant. So the whole for loop is big O of n, and our solution has linear time complexity. If we used here binary search instead of this constant part, we would have logarithm n, so it would be O of n times logarithm n. And if we used here linear search, it would be another n iterations. So it would be big O of n times n, which is quadratic time complexity. But here we have only linear time complexity. Space complexity is linear as well because of a dictionary, and it's possible for an element to create n key value pairs in memory. If we have some duplicates, it would be less, but in the worst case, it's possible to have n insertions in dictionary. So to summarize, with this solution, we have big O of n time and big O of n space complexity. With linear search, we would have quadratic time complexity, but constant space complexity. And for the binary search, we would have O of n log n time complexity and constant space complexity. So this solution is the best in terms of time complexity and the worst in terms of space complexity, but time complexity is much more important, so this solution is considered as the best between these three solutions. Let's see which topics we covered today. We talked about different arrays, dictionary. We applied iterative brute force solution. We discussed add operations to our dictionary and how to check if dictionary contains appropriate element. We discussed different searching algorithms like linear and binary search, and also special case when we are searching by using the dictionary. We discussed also both time and space complexity. As explained, time complexity for the last solution was linear as well as space complexity. But for remaining two solutions, space complexity was constant. For linear search, time complexity was quadratic. And for binary search, time complexity was n logarithm n.